So I'm Joe Neer. I'm a postdoc at UC Berkeley working with Don Song. And this is joint work with Noah Johnson and Don Song. So we're kind of working towards, in general, trying to be able to answer SQL queries with differential privacy. What I'm going to do in this talk is I'm going to focus about as much on our experience in kind of getting to the point where we can do this for as many real-world analysis tasks as possible, as much as I am about the actual work. So I'll go over it, but kind of at a high level. I'll put a link to the paper at the end, and there's lots more details there. But the kind of general outline is I'm going to talk about kind of how do we arrive at this problem first, and then I'm going to talk a little bit at a high level about what our solution actually looks like, and finally I'm going to spend quite a bit of time kind of talking about our experience and kind of my opinion and my speculation about what can help us be successful at this kind of thing in the future. Okay, so we have this collaboration with Uber, and that's really what kind of sparked a lot of this work. We started talking to Uber, I guess, more than a year ago now, and they said we want to be able to have a system that we can use to deploy differential privacy. And in fact, they wanted to be able to use differential privacy in a couple different ways. First of all, it turns out Uber is a very big organization, and they don't always have a complete trust in all of the people working for them. They have a lot of customer service representatives, for example, that have to look at data about customers to do their jobs. And there have been some cases where some of those customer service representatives have abused that access, right? And so there are cases like this that they're worried about. And they're also worried about cases where they're sharing data externally. This is one of the things that was a little bit of a surprise to us. It turns out a lot of the parties that they're sharing information with are subject to Freedom of Information Act requests. And so even if Uber trusts the people they're sharing the data with, it's often, in order to operate at this airport, we have to share information about Uber's operations with the municipality that has that airport in it, right? And now that data is sitting in kind of this governmental institution, and they can get Freedom of Information Act requests. And so Uber would really like to be able to protect that data as well, even if they trust people at that organization to keep it private. And so we went into this kind of looking for use cases, right? Looking for use cases in data. We wanted to figure out what people actually care about, what their utility goals are, what their privacy goals are, and can we build a system that can actually meet all of those goals and provide differential privacy at the same time. And so one of our big goals going into this was, can we write some open source code that will kind of act as a starting point for other people who also have goals like this, other organizations, other companies, and other people who want to build upon this stuff to extend the system to support more things. So we kind of looked at what was out there already, and this is in fact what Uber did also before they started talking to us, is they said, is there something out there we can already use, right? And there's been a lot of theoretical work. There's been very successful deployments of differential privacy, kind of targeted at specific tasks, right? And so for an organization like Uber, they looked at this and said, that's not really going to work in our case. And in fact, we'd almost be starting from scratch if we took one of these systems that's tailor-made to a specific application. And so, this is kind of, in general, we think, one of the reasons that there hasn't been more movement towards deploying differential privacy solutions, right? In terms of code especially, if you want to build a large-scale deployment, you kind of have to start from scratch, right? I know that's a generalization, but that's kind of the attitude that we saw when we started this with Uber. Okay, so we kind of set out to say, can we build something that's a little more general? And of course, there are going to be corresponding limitations to that. But can we look at the kinds of questions that Uber's actually trying to answer with their data? And can we see what is kind of the largest set of those queries that we can answer with differential privacy? And so we started to look at what are the actual queries that they're interested in. And so we were able to get about 8 million SQL queries that were written by analysts at Uber. And we did this study. They're from a lot of different parts of the company. They use these queries to do fraud detection. They use it to do marketing. They use it for all kinds of stuff. And we wanted to figure out what would we have to do to build a system that would be able to answer as many of these queries as possible with differential privacy? And so I want to give you just a sample of a couple of the results of that. First of all, the majority of queries, the most popular aggregation function that's used in these queries is count, right? So counting queries are pretty popular. There's also a lot of sum queries. And there's not nearly so many average and max and min queries, right? And so we started to look at this and say, well, we probably should try to support these. We probably don't care as much about these, right? The other thing that we found, and this was a surprise just how prevalent this was to us, is that there's a whole lot of joins in these queries. I guess it's not a big surprise that it's relational data. If you have data stored in multiple tables, you're of course going to want to do joins. But more than half of the queries use joins, right? And a lot of the queries. So this is kind of a histogram of how many queries use how many joins. So there's a lot of queries that use 0 joins and a lot of queries that use a small number. But there's also queries that use upwards of 100 joins. And what we found is that these queries are kind of some of them are programmatically generated. Some of them are actually typed in by analysts to a tool that they use to submit queries to the database system. But it looks to us like, and from the conversations we've had with some of the analysts that wrote these queries, they're kind of built up by copying and pasting little building blocks, either from other queries they've run in the past, or kind of repeated metrics that they're copying and pasting, and each one of those metrics forms one column in the output, right? And so these queries get really big, right? And we need to be able to answer these big, complicated queries. And this turns out to be a systems challenge as well, and I'll talk more about that in a little bit. But kind of the basic result here is we have to be able to support joins. And the final thing, and this turned out to be a big systems challenge as well, is that there's a lot of different databases being used at Uber, and we think this is probably the case at a lot of organizations. The kind of net result of this is we really can't replace the database engine with something else. In general, we really can't make significant modifications to it. These databases, typically they're deployed for a specific use because they are tailor-made for that kind of application, right? One is good at one thing and another one is good at something else. At Uber, for example, they use a Hive database for queries that need a lot of memory, and some of these things run for days. And in other cases, they have queries that they want to execute in minutes and get results kind of in real time, and they have a different database for that. And so we really can't disturb that picture, right? These things, it's been hard enough for them to get this to the point where they can even answer the queries to begin with. And so we'd really like to be able to build something that doesn't require changing the database. Okay? So the thing we actually came up with is called elastic sensitivity. And we've used it to build a system that can kind of satisfy these requirements. And so before I get to what that is, I want to kind of tell you about the issues with the kind of basic approaches to this that we already know about. So global sensitivity is a measure of sensitivity for queries. And the problem with global sensitivity is that it's unbounded for joins. And I'm going to give an example in a few minutes of what you actually have to do for a query with joins, a simple example that will kind of show you why this is. But in general, with global sensitivity, you are looking at the sensitivity given any two neighboring databases. And so because you can't say anything about what the data is in those two databases, you can't bound the sensitivity of a query with joins in it. So in local sensitivity, you actually get to fix one of those two databases to be your true database, the one you actually have. And so this, with local sensitivity, you actually can use properties of the data in your actual database to put a bound on the sensitivity of a query with join. The problem is that the definitional way of doing this, right? You wouldn't actually do this, of course, but what the definition says is look at every neighboring database of the one you actually have and run the query and look at how much the results changed, right? So obviously we can't do that. So elastic sensitivity is basically just an upper bound on local sensitivity, right? All we wanted to do is come up with a way to approximate local sensitivity without having to do all this computation. And so elastic sensitivity can support joins. And the insight here is that we can bound the sensitivity of a query with joins based on the multiplicities of the join keys that are used. And I'll show an example of this in just a second. And so all we need to know is the multiplicities themselves. So we can ask the database for what those are. And we have ways, although I don't want to claim too much here, of supporting aggregation functions other than count. Count definitely works the best. We have ways of supporting some, although depending on the kind of size of the population you're considering, it doesn't work so well. We've also done some kind of preliminary experiments with trying to support averages and stuff like that, and we don't have a great solution for that. But this is something we're interested in working more on, right? We're kind of starting with counts and trying to move as much as possible towards supporting more and more kinds of SQL queries with good utility. So I guess the other thing that I should point out in general here is that we're not necessarily going to be able to produce optimal utility for any query, right? We have what is essentially an upper bound on local sensitivity, and in a lot of cases is not a very tight bound. And so really our goal here was to build something that we could actually deploy that's computationally efficient and that would support a large range of queries. And we know that it's not going to be optimal in a lot of cases. Yes?
So I'm guessing that all of this will work if your joins are on attributes in base tables, right?
Yes?
Because you can't know what the multiplicity is for attributes of derived tables, which are subqueries in your original query. So in that case, you won't be able to estimate a bound on the elastic sensitivity. So what fraction of the queries that you looked at, right, had joins that were not on base table attributes?
Right. So the question is, you have to know the multiplicities of the keys, right? And so if you're doing a subquery, you won't know the multiplicities of the keys, so you can't handle a query like that. The answer is it depends. In some cases, you can know the multiplicities of the keys. If you have a query that, say, produces a table of counts and then joins on the count itself, we can't figure out the multiplicity of the key there, right? If you have say, one table that is the join of two base tables, and then you want to join just on that result, we can figure out the multiplicity there. We did a quick study of this and found that that's less than 1% of the queries do the first thing, the thing we can't handle. So yes, there's definitely queries like that we can't handle, and at least in our data set, they don't occur very often in practice. OK, so here's the example I was promising. So imagine I have these two tables, A and B, and I'm taking the join of them. And so what's going on here is I have two ones in the B table. And so I get two duplicates of that A value in the join, right? Or one of them is a duplicate. I get two copies of it. And so if I'm trying to find the local sensitivity of this, what's the worst thing I can do to this database to increase the size of this join? Because my query here is a counting query. And the answer is I can add something to A. And for every row I add to A, I'm going to get two copies of it because of the two ones in B. So as long as the key here is a 1, I get as many copies as there are in B. And so that's the local sensitivity here is 2. But the kind of general insight here is that in general, the local sensitivity is bounded by how many copies of this 1 there are, right? And in global sensitivity, you don't know anything about A and B, right? In global sensitivity, you have two databases that are neighbors, but they could have anything in them. In particular, this B table could have 10,000 ones, in which case the local sensitivity would be 10,000, right? And so we need something like local sensitivity that lets us bound the number of ones here. OK. Yes?
So I still didn't catch, how do you calculate this upper bound in a differentially private way?
Right. So this is one of those details that I wasn't going to talk about. So the issue is local sensitivity is itself can leak information about privacy because you're calculating it based on your true database. And so you have to do something. You can't just add noise based on the local sensitivity. And so there's several different things you can do. The one that we have used in our experiments is called smooth sensitivity. And so basically, smooth sensitivity says, I'm not going to look just at the local sensitivity at this database, but imagine I have databases that you could construct by moving k steps away from my database. And then if there's a big jump, say 5 steps away, then you have to smooth out the actual sensitivity you use to account for that. And so we're using smooth sensitivity. OK. So we built a system for this, right? This turned out to be one of the more challenging pieces because we have queries that kind of look like this. So this is an example of a query, and there's like 10 more pages like this. So a lot of these are like thousands of lines long, and they use all kinds of SQL features that I didn't know about going into this, and that it turns out do different things in different database engines, and it's sometimes hard to even figure out what the semantics of the thing is. So the queries turn out to be really complicated, and even just figuring out what these queries do and being able to write a program that will read them in and do some kind of analysis on them is pretty hard. And so what we did is we built this framework for essentially doing static analysis of these queries. And we wanted to solve this kind of complexity once, convert this big monster into some kind of a representation where we could run analyses on it very simply. And we could write new ones. So not just for differential privacy, we've actually used this also to do things like figure out which columns of the output of a query might have personally identifiable information in them and strip it out. So our hope is that you can do lots of stuff with this framework. And so we use that to build a system that kind of looks like this. So you have an analyst that writes a query, and it gets sent directly to the database. So this is an unmodified database. It's the one that's already there. And you get out some sensitive results, right? So these are not differentially private. You also send this into our analysis framework that has an analysis for calculating the elastic sensitivity of the query. And the result of that is the elastic sensitivity. It's just a number. And you give that to this output perturbation step along with the results of the query. And that thing generates Laplace noise and gives you the differentially private results. Yes?
So it looks like the data doesn't get to the analysis framework.
The data doesn't get to the analysis framework, but you have to know something about the data in the analysis framework. Yeah. So I think that's what you're getting at here. Yeah. So
that was my question.
So the picture is slightly simplified. Depending on how you deploy this, you might want to do this in different ways, right? So one way to do this, so the analysis framework needs to know about these multiplicities, right? This is the thing that I mentioned earlier. And so you can either have the analysis framework, have an arrow to the database, so that every time you ask a query, you can have the analysis framework ask the database, what are the multiplicities for these keys that I need to know, all right? That might not be very efficient. What we've actually done at Uber is they update this database kind of on a regular basis, right? And so every time they do an update to this database, we also figure out what all the new multiplicities are and send them to the analysis framework. And so that way you only have to update those every time you update the database. So obviously it's going to depend on what the database environment looks like as to the best way to do that. OK, so one of the cool things about this is we were able to take those queries that I talked about and actually see what would be the effect of differential privacy on these queries, or at least of our approach, right? And so this is a couple of kind of scatter plots that show you for a bunch of queries. There's about 10,000 queries in these pictures. What does the utility look like as a function of how many trips are the queries querying? Okay? And so the general trend that you see is the error goes down as you query more trips, which is what you expect to see. As you get a bigger population, you get less error. On the left side, these are queries that don't have any joins. And so effectively, we can use global sensitivity here. On the right side, these are queries with joins. And you see there's kind of two groups here. There's a lot of queries down here for which we're doing pretty well. There's a whole bunch of queries in kind of a second group up near the top there. And these are the ones where either they're using a whole lot of joins, and so the sensitivity of the query just kind of explodes, or maybe our approach just doesn't work very well, right? Maybe these are queries on tables where the utility that we're going to give you is, in one sense, kind of a direct. It's directly related to what is that multiplicity, right? And so if that multiplicity is really big, then the elastic sensitivity of the query is going to be really high, and you're going to get a lot of error. Yes?
Are you providing privacy for the trips or for the users here?
We're providing privacy for the trips here. So we are definitely not providing privacy for the users here. Yeah, it's not user level privacy. Okay, so I want to talk a little bit about kind of what we learned from this and what we think might be helpful to other people. And a lot of this is going to be kind of my own opinion. And if you disagree with me, then I'd love to talk about it. So this whole project really wouldn't have been possible without collaborating directly with an organization that has access to data like this about what people care about. And so this opportunity to use these real use cases was exciting to us. And this was one of the best parts of this. It also gave us some insight, although I'll talk about some of the challenges of this in a minute, of what the privacy goals are at a place like Uber. And in particular, we were a little bit surprised about this internal versus external question. We figured the external use case would be kind of the obvious one, and the internal one was a little more of a surprise to us. And the other thing that was really helpful to us is we got to learn really what does the system have to look like from a systems perspective, right? What can you do, what can you not do if you actually want to integrate this into a data environment like the one that Uber has. We had a lot of kind of frustrating or challenging things also, though. I think anybody who's tried to deploy one of these systems at a place like this probably has seen similar things. So one of the things that we tried in the beginning was talking directly to analysts. We would go and have meetings with them and say, what are your goals in terms of utility? What kinds of things do you care about in terms of where do you need the most utility and where are you willing to sacrifice a little bit? And what kinds of privacy goals does your team have? And in a lot of cases, they said, well, we just want to do our jobs. We don't really want privacy all that much. And in some cases, in machine learning teams, we got this response a lot. They seem to think, well, we're doing machine learning. There's no privacy problem anyway. And we had trouble getting traction in these teams, talking directly to them. So we also talked to the privacy team at Uber. And this is the team that we're kind of embedded in, I guess, is what they call it. The problem is the privacy team is separate from all these analyst teams. And the privacy team ends up kind of, in a lot of cases, being the people that go around to the other teams and say, you have to do these privacy things and it's going to make your job harder. And so that makes things difficult for them too. And on top of that, there's the privacy team isn't exactly sure what they're supposed to have as their own privacy goals, right? So there are people above the privacy team who say, we need to have privacy. We need to protect the privacy of our users and stop these essentially bad headlines, right? And then the privacy team kind of has to go and figure out how to do that. And I think in general this is a hard problem. And in a lot of cases I think they don't have the background to even appreciate the scope of the problem. And so these people have the right motivation and they're trying really hard. But in a lot of cases, they're not able to get traction with the other teams either. And the other problem is we can build something, and then the infrastructure teams also see that as kind of another piece of work that they're being asked to do that they don't necessarily see the value of. So we can build something and say, we can give you differential privacy for, say, 80% of the queries. And they'll say, what about the other 20%, right? We can't just fail on those queries. And so it's kind of yet another party that you have to convince of the value of this. And so we've had some trouble with that as well. And one thing we've done here that has worked well, I think, is to build systems that can support lots of queries. They just sometimes don't give very good results, right? And an infrastructure team is more willing to accept something like that, even if I don't personally believe it's such a great idea. OK, so here's the really speculative part. So these are my conclusions. So here's what I think. These are kind of the lessons that I've learned about how I think we can move things forward a little faster. So the first thing is I think it is going to take time. So at Uber, we're kind of working towards a deployment of a system based on elastic sensitivity. What they'd like to be able to do at Uber is to, they have this it's basically like a web portal where you can go and you can type in a query. And they'd like for one of the options there to be, give me differential privacy. And they'd like eventually for at least a subset of their analysts that use this tool to be able to, for them to have that turned on by default. And if they really need the answer to a query, then they push a button that says, give me the real answer. And then their manager has to, later on sign off on that, right? And so we're working towards that, but it's kind of slow, right? And I think we'll get there eventually, but a couple of things, it's the first versions of this, I think, are going to be kind of limited, right? The first version that they're targeting, at least, is, let's just make it an option for people who want to try differential privacy. They can turn it on, and so, I think it's just going to take some time. And the second thing is we're going to make some mistakes, right? So, of course, I personally am very worried that I will introduce a bug into the system that will cause privacy to be broken. And I try not to worry too much about that because I just know it's going to happen at some point. Even if I don't make that mistake, somebody else who's working on the code probably will. And so I try not to worry too much about it because, in my opinion, it's better than not trying to have differential privacy, right? So the second thing is I think we can accelerate this progress, as academics we can accelerate this progress by being encouraging of people who are trying. And so I think constructive engagement is a good idea in the sense that if an organization is trying to deploy differential privacy and maybe they're not doing a good job of it, as long as they're being transparent about it, we can suggest how they can do a better job. And I think we should try to be constructive in that way and not be negative, not say, oh, you're doing a bad job and you should just give up and not even collect this data, right? Instead, let's try to say, here's how you can do a better job of this. And I think the kind of other really important piece, and this is maybe the one place where I would say, I would reserve my harshest criticism of somebody trying to deploy differential privacy for this case. I think transparency is really, really key. I think we can't ever really get privacy value from a differential privacy system unless we know what it's doing. And so I believe in releasing code. So we have our code here. We're releasing more of it all the time. I'm sure there's still bugs in that code too, and so we welcome feedback on that. If you find bugs in that, we've already found some and had feedback that helped us find some bugs in the code. And I think that's a good thing, right? That's kind of how it's supposed to work. That's the process that we have to go to kind of eventually arrive at a point where we have really robust systems that we can trust to give us privacy. So I've also got a link here to the paper describing elastic sensitivity, and that's my email address. If you want to talk more about this or know people who might be interested in talking about this, we're always looking for more use cases and more people who might be interested in exploring deploying systems for differential privacy. So I'll stop there, and I'm happy to take questions.
We have a minute or two for questions. Yep, absolutely.
So you started out kind of lamenting the sort of lack of general purpose kind of differential privacy solutions, like that Uber can just download something and start using it. But in your remarks towards the end, you talked a bit about needing to understand the requirements that may be very specific to a company or organization that wants to use differential privacy, which makes it harder to imagine general purpose solutions that could port from one set of hard requirements to another one. So do you have any kind of thoughts on the balance between these two?
Yeah, so this is a very hard problem, I think. I think there's part of the issue is that there's a number of different kinds of requirements. I think there are some requirements that are kind of common across organizations. I think this need, for example, to not modify the database is probably a pretty common one. I think there are a lot of other requirements that are really specific to a use case, especially when it comes to the privacy goals that they have and the utility goals that they have. And there, our work isn't really looking at those yet, right? What we've tried to do is kind of look at SQL queries and see how many we can answer, right? I think probably the best thing that we could arrive at is kind of a framework that people could use to build something more tailored to their use case, but that will not let you violate privacy, right? So somebody who doesn't really understand how to, write a proof, for example, that their system preserves differential privacy, could still build something that would work really well in their use case. And so, I think that there's some really good work going on towards that at Duke, for example.
Well, and maybe certainly philosophically, that was the motivation behind Pink, which is now this system that Frank McSherry wrote, which is now getting close to its 10th birthday.
Well, and Pink is a good example because we talked to people at Uber the first time. They said, we know Pink, right? Everybody knows about Pink, and they've looked at Pink much more than they've read papers. So, yeah.
So I was curious to hear your thoughts about these 20% of queries. Is it kind of a hopeless case, or can we hope to maybe develop better differentially private algorithms that might handle some of these queries in the future?
So the 20% number was kind of a ballpark that includes lots of different things. There's a whole lot of queries that really aren't statistical in nature. They're really looking at, I want rows, right? And there I think we don't have a lot of hope. There's other queries that, as Ashwin asked about, the query includes something that we just don't handle yet, and you could definitely come up with an algorithm that could handle them. And so I don't know kind of what the breakdown looks like. But there are definitely cases where we could push that number up, yeah.